practice midterm kind of thing?
I will probably not put up a practice midterm, but we will discuss what's going to be on the midterm. Your practice effectively is the two lectures that we've had and
One homework assignment.
the one homework assignment. Yeah.
And we will not be able to see the previous midterms to see what,
So that again. Well,
will we not be able to see previous midterms, like the ones that we had last year?
you'll probably not be able to see previous midterms.
It's really sad.
Yeah. Life is sad sometimes. It's not that sad.
So,
Okay.
actually,
Should be recording. Yeah, this whole, the midterm being so soon is odd. I'm not gonna, but you know, what that means for you is that it can only be so hard because we've only covered so much. And so the idea is not to fail you or to swamp you, but you know, to kind of draw the middle ground as to where you should, you know, how you should be doing that we expect will correlate with your kind of end performance in the class. And so if you feel like you're totally over your head, you know, now's the time to reconsider. You know, as far as I'm concerned, I don't think anybody should be way over their head. And so unless something really, you know, kind of motivates you to quit now, I expect everyone to remain. But that said, I wanted to kind of squeeze that in midterm before the drop date. Yeah.
I don't know how to put this in words, but like would homework 1 be covered in terms of the range wise cover the stuff that we need to know in midterm 1?
Yeah.
Okay.
So effectively it'll be homework 1 and whatever we get through on Tuesday.
Okay.
That's really what's going to be on there. So, you know, the lectures leading up to Tuesday, through Tuesday, and the homework that you've had.
Okay.
It's not that much.
Right.
There's only so much I can do to you. So, yeah.
so the midterm will obviously be harder than homework.
Not necessarily.
Oh, okay.
I mean, actually, there's an argument to be made that it should be the other way around, because you have a week for the homework, you have time to carefully, calmly sit down and think. That time doesn't exist in an hour, and so I cannot ask you, for example, questions 5 and 6 that we have in the homework that's totally inappropriate for the midterm, so I wouldn't necessarily say that. But people have gotten the homework? You saw it, who made the suggestion of putting in the assignments? I followed through on that and I think it worked. Somebody said if you put in the assignments, everybody will get a notification without my having to do anything else. I think that's how it worked.
Yeah.
What?
I didn't get a notification, but I saw it on like Canvas.
You didn't get a notification?
I think it's
I heard
good,
it off.
change the settings, because I changed my settings so I got one.
Who else did not get a notification? Oh wow.
Because that's to do with the settings.
Yeah.
Okay. Do you guys know what you need to change for that? If you run into issues, let me know, because I want to make sure that you're getting these things and not, you know, are not forced to check on yourself. Even though you should be. Okay, let me go see if there's anybody else there, and I'll help you. Just try to be in the middle, roughly.
No, we can move it.
Okay. So, multiple things I need to say before we really get going. One, some things will feel a little disjointed because I want to cover a couple of areas, and I also don't want to dive too deeply into kind of some of the more really important areas that I want to start tomorrow to make sure that people that we're missing, even though they're going to get the recording, kind of get a full picture too. So I apologize for that, but let me just start off with a couple of homework tips. The homework has been posted. It'll be due at 5 p.m. next Tuesday. You will most likely, and I have to finalize this with our TA Sarah, you will likely be submitting it into her mailbox. And so there's a way to just drop it in. She will come and pick it up at 5. She might be 5 minutes late, she will not be 15 minutes late. And so make sure to get it in there on time. Don't want to have to deal with cases of late homework. Okay, homework tips officially starting. Only 2 problems are the ones that I want to give you a couple of hints on. Problem number 2, you're asked to evaluate the probability that the drunk, can't remember exactly how it's phrased, comes back to the origin, comes back to the lamppost, right, after a certain number of steps. And the 2 scenarios are in A, I believe it's an even number of steps, and B, it's an odd number of steps. Obviously, we're dealing with an abstract number of steps, or we haven't said he makes 10 or however many, it's just some number n. For the even and the odd, don't jump too deeply into calculations first. Stop and carefully think about the problem. One of those answers is It does not need to be numeric. And you can just arrive at it by thinking carefully, not particularly hard, but carefully about the problem. So don't go like gung-ho on the math and what's the formula that I'm going to write down? What numbers do I plug in? Stop and think about it a little bit, and I think the answer will come to you. One of the answers will be trivial once you think about it enough, and the other answer, because I don't give you what n is, the total number of steps, will have to be written in terms of n, so don't be perturbed by it. One of your answers will have n in it as a number that hasn't been specified. Number 5. It's kind of a long one. You're given this relationship, which you can certainly justify or show to yourself to be the case. And that is that if you have an expression that looks like this, where n is some number, and specifically the number that is being summed over, and p is the probability to make a certain step or observe a particular event in this binomial distribution kind of sense, what you're told is you're going to have to use this expression. There's nothing fancy about this. If you just do the derivative, you can prove to yourself that the two have to be equal. And the question is, why is this useful? And the reason it's useful is because what you're really going to be dealing with is not just a single term like this, but a sum on n. In the sum, among other things, will be a term that looks like this plus other stuff that does not have p in it. And so if I just go ahead and replace this bit by that, what I end up with, and let me just forget about this for now. Spill my oils all over the board. This is going to look like this. All I'm going to do is I'm just going to plug this in for that. ddp is, of course, a partial derivative. Something like this. So the hint that I want to give you is as follows. The only terms that really need to remain in the sum are ones that depend on the index n. Where p is by itself, not raised to the power of n or anything else, is effectively a constant as far as summing over the index n is concerned. So what does that mean? You can put it outside the sum. Similarly, this derivative with respect to p is with respect to p and not with respect to n. And one thing that you might remember from calculus or quantum mechanics is that derivatives are linear operators. A sum of derivatives is equal to the derivative of the sum. This is a sum of derivatives. You can convert it into a derivative of the sum because ddp does not depend on n itself. And so you might write this as p having been brought outside the sum, ddp also being brought outside the sum, sum on n, everything else that depends or has n involved in it somehow, and that's p to the nth power. So that's the totality of my hint. This is an algebraic manipulation that you should use, or will have to use, to get to the right answer. Yeah?
Will you be covering the Taylor series that you talked about in number 4? Question number 4.
Will I be covering it? No, because it's not actually part of the problem. I just force you to kind of extra credit wise without any extra credit to think about it and to make yourself comfortable that you can understand where it comes from. You're not getting points for it, but that said, it's not a bad thing to understand how it works. And so try the Taylor expansion yourself. And if it doesn't work, come see me and let's talk about it and make sure you get to it. But I think it'd be easier, or not easier, more effective if you gave it a try first. Even if it's not part of the problem, that's going to be great. Yeah?
For going back to number 2, for the trivial,
Yeah.
For the trivial answer, can we explain in words?
Yeah, absolutely.
Okay.
That's what it's going to have to be.
Okay.
So it sounds like you found the answer. Yeah. Any other random questions about this? So those are the homework hints. Yeah?
Can you use a different pen perhaps, like a black pen maybe?
Yeah.
Hard to see.
I can.
Thank you.
Should we vote?
I agree.
You're worried about the green? You want the black?
I just want dark colors.
I don't know if green's going to be that much darker. Let's go. Yeah, it is quite light. Can you see it actually? Should I rewrite it or can you guys make it out? Yeah? Okay. I'll switch from that one. Okay, let me talk about the midterm really briefly again. So, we talked about the fact that there's only so much that we've done as it stands. And it's coming really soon, I know all of this. So what have we covered? We talked about probabilities, kind of a couple of simple rules, multiplying probabilities, adding probabilities for mutually exclusive events. That's fair game. Homework problems are fair game. And so, instead of just getting the right answer on the homework, you should really make sure that you understand these problems. And if you don't understand something or some manipulation, I want to come talk to you. Or rather, I want you to come talk to me. We have office hours on Monday. Because I missed my office hours this week, it's probably more effective if I just put in an extra set of office hours right before the midterm. It won't be a review, but it'll be kind of like, hey, come ask me whatever you want and let's work through the problems that are bothering you. I don't know exactly when that'll be, but it sounds like it might be a topic of discussion or announcement for Canvas. I'll figure that out. So, what else? The concept of permutations versus combinations. So ordered arrangements versus combinations of objects. And we'll have more to say about this today because I feel like it's a topic that's a little bit unfamiliar to people, this whole idea of combinatorics, of counting certain combinations and arranging objects in certain ways. It's a little weird if you haven't seen it before. The binomial distribution is also fair game. You have homework problems on it. We covered it in class. So understand what it means, be able to work with it. For example, on the homework, I think problem 5, you are given the formal expression for the average value or the average number of steps to the right within the binomial distribution kind of world. So if I asked you to calculate the average value of number of steps to the right after 5 steps, so now being concrete about our numbers, you should be able to do that calculation. And you should stop and think about what that means, what it will entail. So these kind of things I would like you to be familiar with. What's that?
What you just said, if I asked you to calculate,
if I asked you to calculate the average number of steps to the right after
5 steps.
10 or 5 steps, you should be able to do it, you should be able to write it out explicitly. And, sometimes staring at a formula, you might convince yourself that you know how to do it explicitly, and then in practice, it kind of, you find that there's certain levels of comfort that you haven't attained yet. And so try it out, play around with it a little bit. I don't know how useful that statement is, play around with it a little bit. I don't know how many of you are going to play around with it, but okay. And again, what we will get through on Tuesday will be fair game again. My point is not to introduce this insanely complex concept on Tuesday and be like, okay, good luck. I'll try to be gentler than that. But that said, that material will be fair game. It's not going to be intellectually different from what we've done so far, so we'll talk about probabilities in a slightly different sense and so on. So that's about it. That's all I wanted to say about the midterm. So let me now do a couple of problems that kind of come back to some of the issues that we've been dealing with. And that is this idea of counting and distributing objects among different bins. And as I mentioned before, it's not entirely clear what this has to do with thermodynamics and understanding thermodynamics from molecular properties, but you will see how this kind of comes out. And especially if you've been reading Terrell Hill sections 1 through 3, you will have probably seen some flavor of this. Okay, so what I want to do actually right now is a worked out example in your book. So this is Macquarie, Math Chapter J, Example 1. So this is example J1. And it's worked out, so you can go back to it, and we're going to reproduce it, but I also want to say a couple of words about it. So Macquarie, that's not that much better. Macquarie, Math, Chapter J, I believe it's example 1, but if it's not 1, you'll quickly recognize it once I write it down. Here's the question. Calculate the number of ways of arranging or combining 4 distinguishable objects, objects that you can color or possibly number in some reasonable way, distinguishable objects into 2 groups containing, this is verbatim from the book, 3 objects in one group. Let me just write it out. One group. I apologize for my ridiculous handwriting, but you're going to have to live with me. One group and one object. Object in the second group.
So we have two groups or two bins, you have 4 objects, and the question is, what are all the possible combinations of objects, or all the possible ways that I can distribute them such that, and that such that is important, one of the groups contains 3 objects, and the other one contains 1. This is what is known in this business as a distribution among the different bins or categories, however you want. And so what we talked about in class is that we define this idea of a statistical weight of a distribution. Another way to say it is how many possible ways can I achieve a given distribution given that I'm dealing with a certain set of distinguishable objects. And by the way, as a little aside, it might not be clear to you what exactly we mean by indistinguishable object, and that's okay. We'll come to that later in the course. It's kind of a deep quantum mechanical point. For example, electrons are indistinguishable. Other fundamental particles are indistinguishable. Balls that can be colored, or big things that could be arranged in some specific order are distinguishable. You are distinguishable by your face, for example, and so on. But there are things in nature that are indistinguishable, and it's going to introduce a very substantial conceptual complication that we're going to have to deal with as we go on in the course. So far, the complication is not there. Okay, so the formula we said is that if you have n objects, and you have to distribute all of them among 2 bins, such that one bin gets n1 of them, and the second bin gets n2 of them, of course with the condition that the sum of these 2 objects has to be equal to total, because you're distributing all the objects. This was the formula. And so we can chug through this formula, but then I want to write down exactly what we mean by this. You know, this seems a little abstract, and so in our particular case, what do I write? What's the total number of objects? 4 objects, so 4 factorial divided by what?
3 factorial.
3 factorial times 1 factorial, and if you write this out, this is 4 times 3 times 2 times 1, divided by 3 times 2 times 1, and then times 1. So this whole thing cancels, and the answer is 4. Okay, so that's the algebraic way of finding it. Now can we justify to ourselves what are the actual arrangements that we're talking about? And so what McCory does is let's label these objects as A, B, C, and D. Just give them some labels. You could have labeled them as 1, 2, 3, and 4. Just might get confusing. So we have objects A, B, C, and D. It might be 4 different colored balls, whatever you want. And so what we're talking about is 2 bins, where one bin is forced by the setup of the problem to contain 3 objects, the other one can contain 2. And the question is, can we actually write these down and prove to ourselves that the number ought to be 4, even though the formula says it should be? And so what are the possibilities here? Well, A, B, C, and D is 1. Just gonna write these down. A, B, D, and C is another. A, made a mistake in my thing, but I think I just corrected it.
No. A, C, D, and B.
Oh. A, C, okay, not corrected. A, C, D, B, the last one. B, C, D, A. Does everyone agree with me? This is what we mean. This only makes sense if the objects are distinguishable, so you can actually say what they are. Notice what we don't care about. We don't care about the fact that A goes first, B goes second, and C goes last. If we did care about that, for example, if A, B, C was different from A, C, B, what are we talking about then? Not combinations, but what? Permutations. An arrangement having a very specific order. Whereas here, we're talking about just a collection of objects. And so I want to make that clear. Let's list a couple of permutations of these guys, for example. Just so it's clear. So what are the different permutations? If we're sticking to just this top line, we're going to leave D alone because it's just the only one. And so we're talking about permuting just 3 objects, right? And so how many permutations do we expect? How do we figure that out? We have 3 objects in the left bin, and we want to permute them in different ways. How do we know how many permutations are there? 3 factorial permutations. So we expect 6. And so let me just write these permutations down. Again, maybe I won't do all of them because you get the point. So A, B, C, A, C, B. Again, D gets left alone. C, B, A, D, and so on. And you can fill in the other 3. And so again, I want to point out the difference, that I want this to be clear that here, the idea is that we don't care about the actual arrangement. All we care about is who made it into this bin and who made it into that bin. And so what I want to do next is kind of a really trivial extension of this, is to ask the question, how does this look in the language of steps to the right and steps to the left? And so the idea with steps, imagine we're talking about n, so for the 1D random walk problem, if n equals 4, we're really talking about 4 distinct steps, right? So let's just call them S1, S2, consistent, S3, and S4. And then what we really have are 2 bins where this might be left step, this might be right step, and then we're talking about what are the possible combinations for these guys. So one case you might imagine is S1, S2 are steps to the left, S3, S4 are steps to the right. You might also imagine something different. For example, S1 and S3 are left steps, leaving S2, S4, sorry, I'm not consistent with my subscripts. I think you get the point. Of course, what's also equally valid is scenarios that look like this, S1, S3, and S4. I'm really inconsistent with my numbers, sorry. S2. And so when I ask you for the total number of ways of distributing these objects among these 2 bins, I have to tell you what distribution I'm talking about. And so here the distribution is 2 go on the left, 2 go on the right. So for the scenario that 2 steps go on the left and 2 steps on the right, what is the statistical weight of that distribution? That is to say, in how many possible ways can I have this unordered arrangement, such that this box contains these objects, this box contains that object, or that set of objects, independent of how they're arranged within the box itself. That is to say, S1, S2 is not different physically than S2, S1. And so we would say we have 4 steps total, and for the distribution where it's 2 and 2, you would have 2 factorial, 2 factorial. So this is 4 times 3 times 2 times 1, 2 times 1 times 2 times 1, and so this is 4, cancels that 4, and it gives you a total of 6 combinations, not permutations. Again, it's not entirely clear to you why this is important, but it will become important as soon as Friday. That is to say, tomorrow. So as I warned you guys, I'm going to be choppy, and we may end up early today just because I don't want to overdo it on this kind of lecture that only some people could show up for. And so I'm done with this. I'm done with midterm stuff. I'm done with these boxes and bins, and now I want to go back to the physics of the... But before we kind of make progress, I mean, let's keep the big picture in mind. What we really want to be able to do is we want to say, here's our collection of molecules. Here are their energy levels according to quantum mechanics. We've solved their Schrodinger equation. And now tell me what is the average pressure of the system if I were to do a thermodynamic measurement. It's not clear how to get there, but that's where we're going. Before we go there, we have to establish a couple of concepts or understand a couple of ideas. And one of them we kind of started touching upon is this idea of a many-body energy level or a many-body quantum state. We wrote down the idea that a quantum state, generally speaking, is determined by giving the wave function. And if it's a single particle system, like a particle in a box or a harmonic oscillator, you're talking about just that one wave function for that one particle. But if you have 2 particles in a box, or multiple harmonic oscillators, or many different ideal gas particles that actually can be thought of as particles in a box, and we're going to do that, how do you think of an eigenvalue, an energy eigenstate of a many-body system? It's not entirely obvious, and it's also not something that one gets in a quantum mechanical class on first pass. And so that's what I want to do right now, is I want to look at a very simple example, think about what we mean by a many-body quantum state or a many-body energy level. It's a more relevant quantity for us. And then to extend this very simple example into a more realistic system where you might have a mole of molecules or a mole of gas atoms where the number is astronomically large. And so let's imagine this artificial scenario. We're going to imagine a line where there's going to be a couple of positions. And each position is going to be occupied by a harmonic oscillator. Now, what is the importance of the statement it's occupied by a harmonic oscillator? The only thing that I need from this harmonic oscillator model is that we know what the energy levels are. The quantum mechanical system has been, or problem has been solved exactly for the harmonic oscillator. We know its wave functions, but we don't care about that, but we also know its energy levels. What do we know? What is a special property of the harmonic oscillator energy levels that is not true for any other quantum mechanical system, and in fact is not true for any system in nature that we know of that is real?
Equally spaced.
Hmm?
Equally spaced energy.
Equally spaced energy levels, exactly right. Most of the time, the energy levels decrease as you go higher and higher, or their spacing decreases. The system we think of is something like a hydrogen atom, a molecule. The particle in a box is an even more weird artificial version, and it's one of the very few systems where the energy levels actually get higher, larger apart as you go up. But for most normal systems, bound to normal potential energies, that's not the case. And the harmonic oscillator is not a normal system. It's an artificial model that is appropriate in some cases, and in some cases wholly inappropriate. But that's the idea. We have three harmonic oscillators. They're spaced in such a way that they don't interact with each other. You know, for example, you might imagine that you might have three molecules that are vibrating and they might collide with each other and exchange energy. We're not considering that case. We're considering just three harmonic oscillators that are far enough apart that they don't exchange energy but are still on this kind of artificial line that we've put them on. And so let me write down the energy levels for these harmonic oscillators. So they will all be identical, of the same frequency, and so their energy levels are going to go up in this ladder. Supposed to be equally spaced and of the exact same magnitude. This oscillator is going to have some natural oscillation frequency, which means the energy level spacings are going to be h nu naught, or this nu naught is oscillation frequency. And then of course the spacing for the next two energy levels is going to be twice h nu naught, so it scales linearly with the number of energy levels. And they're all identical. Now imagine that somebody told you and said, look, I'm going to give you a total constant energy amount. And you're going to distribute that energy amount between the different oscillators. So first statement that we make is that the total energy of the system is going to be the sum of the oscillator 1, oscillator 2, and oscillator 3. And so E1 plus E2 plus E3. I don't mean to raise it to that power, I'm just labeling it. And I'm going to, I don't know why it's NMZ, that doesn't make any sense. Okay, right. So the total energy is the sum of all the energies. And I'm telling you, somebody came and said, look, here's your allowance for the day. Your E total that you get to distribute among these oscillators is going to be equal to, let's say, 4 h nu. So we're going to be counting in units of energy level spacing. So there's 4 units of packets or quanta of energy that we get to distribute among these different, among these three oscillators, among the different states. What are the possible ways to divide this energy? What's the most greedy way? One gets all the energy and everybody else gets nothing. So you might imagine that, 1, 2, 3, and then if I wrote down other ones. So one way of dividing it would be 4 for 1, 0 for 2, 0 for 3. So one possible subdivision of energy. Division of total energy. What's another possible division of total energy? Give me some.
1, 2, 1.
2 for 1. Oh, you said 1, 2, 1? Okay. 1 for 1. 2 for 2. And 1 for 3. All of them giving the exact same total energy. Does that make sense? So the first statement is there's many different ways of dividing a total amount of energy among the different particles. In the simplest case, the particles are all identical. They have equally spaced energy levels. Each possible way of dividing this energy among the different particles is called a different many-body quantum state. That's what we mean by the statement that there are different many-body quantum states, all corresponding to the same total energy, but giving you a different distribution of that energy among the different molecules. And every possible way that I can divide this energy corresponds to some possible way of division, therefore, some possible quantum state of this artificial three-harmonic oscillator system. The place where we're going to take this idea is, for example, a gas of molecules containing a mole, and some total amount of energy being distributed over a mole of molecules. And if that energy is large, and the number is huge, and it is huge, the number of ways of doing that is going to be enormous. And so for a real system with a real fixed energy containing a bunch of particles on the order of Avogadro's number, the number of quantum states consistent with this macroscopic state being the total energy is this. The number of microscopic states or quantum states is going to be some large number. Another way to say it is that many-body quantum mechanical energy levels are highly, highly degenerate. Each different quantum state corresponding to the same total energy corresponds to a different subdivision, a different handout of energy among the different parts of the system. Whether it's gas molecules or water molecules that are liquid, or solid molecules, whatever you want. And for example, as much as this is artificial, it's not that artificial. This is a reasonable approximation for a one-dimensional crystal. Because when you work through the math of a one-dimensional crystal, what you find is that each single vibrating bond can be thought of as an independent harmonic oscillator. Of course, one has to introduce this idea of a normal mode. And it's not regular single oscillator vibrations, but it can be thought of that way. So let me say this again. That we know how to think about energy levels for single systems, and now we have at least come up with one way, or the way, of conceptually thinking about energy levels of a multi-particle system. And if the systems themselves, the subsystems, the individual pieces, don't interact with each other, the energy level, again, still a quantized quantity, the energy level for the whole, the entire supersystem, is going to be equal to just the sum of the individual energies. And if this is true, then as I choose how I divide my total among the different guys, even though they all will give me the same total energy, the quantum state of the overall system will be different. Why is the quantum state overall different? Because, for example, one way to think about it is the wave function for each harmonic oscillator changes with the quantum number. And so when I say that 4 units of energy are given to oscillator 1, that oscillator 1 will be described by the quantum mechanical wave function corresponding to energy level 4. Every other oscillator will be described by the wave function of the ground state. If I give 2 and 2, 1 and 1, then correspondingly, some oscillator will be in this individual quantum state, the other one in that individual quantum state, giving you a different many-body quantum state. But what you mean by different many-body quantum state is, let me look at each individual subpart and ask the question, where are you? What quantum mechanical state are you? And the collection of all the guys and all of their quantum states is the collective many-body quantum state. And so, if the number of system goes to infinity, which is the appropriate limit for thermodynamics, in fact, almost everything in this class we'll be doing will be relying on the assumption, which is basically correct, that the number of systems are going to infinity, or at least in certain cases we'll just be allowed to do that, mathematically speaking. And E total is large. This leads to a huge number of, parentheses, degenerate, corresponding to the same total energy, quantum states, also known as microstates of the system. As opposed to the macro state, the macroscopic state, where each one of these different divisions corresponds to the exact same macro state, because the macro state is the total energy of the system. And when we go on further, it will also involve the total volume of the system, and the total number of particles, and so on. But so far, the macro state is identified in this example by the total energy. Because the total energy in each different subdivision is the same, the macro state, the macroscopic state, the thermodynamic state is the same. The quantum mechanical microstate is not the same. So that has really important implications for us. So let me start setting up where we're going from here. Sorry. Oh my god, I hoard napkins and I have no napkins in my
There's
place.
some tissues in there.
I know myself. I'll deal with it later. Has anyone had a chance to look at Terrell Hill's book? To read sections? Thanks for being honest. To read sections 1 through 3. You know, I will say that it's not always easy reading. That said, when you read it a couple of times, I think it becomes easier. You know, it is an introductory textbook, but it's a hard introductory textbook if you're not familiar with that stuff. And for example, when he goes on to say, here's the statistical weight of the distribution, it just comes out at you without any anything else. Which is why we're doing all of this business to get up there, so it's a little smoother. But it's tough. And so it is what it is. Okay, so now I want to start talking about how we actually describe thermodynamic systems. Where is all of this going? What's the point? And the idea or the concept that we're going to be exploring quite a bit, that basically will set up, will effectively allow us to make as much progress as we possibly can, is this idea of the ensemble, the thermodynamic ensemble, or also known as the Gibbs ensemble method. Who's Gibbs?
This is like count or something.
It's a good guess. Most people of that age were some kind of counts with their fancy laboratory in their castle.
He wasn't.
No. Josiah Willard Gibbs of the Gibbs Free Energy is considered by most to be the most famous American scientist of all time. Let me read you a quote of what Einstein said about him. He called him the greatest mind in American history. He invented vector calculus, kind of a random thing. And so he was a mathematician's mathematician. He was also very much a theoretical physicist. He was a proper Connecticut gentleman, doing his work in the 19th century. And he also came up with a graphical method to work through thermodynamics, which has now been, I think, 3D printed in some kind of a cast, showing all these, hyperdimensional surfaces, intersections of them, and showing where the Gibbs free energy is minimal, and it just looks really insane. So he really, invented this kind of a new thing that I think was too complicated to be really fully appreciated and is not really used in this time. But that said, he is probably considered the father of statistical mechanics. Without the Gibbs ensemble method, I don't think there would be such a thing as statistical mechanics. And as much as Boltzmann is associated with statistical mechanics also, and we'll get to that later, I would say Gibbs probably deserves a much bigger fraction of that. Very, very proper American gentleman. Always wore a nice hat. Okay. So, but also kind of boring, but worth knowing about. Not nearly as flamboyant as someone like Einstein or Richard Feynman, for example. Which also, you probably have to put Richard Feynman in that pool of greatest American scientists. Okay, so we're going to do a thought experiment. Before we do a thought experiment, let me say one thing. When we think about a macroscopic system composed of some number of particles and some volume, or let's say it's a bunch of gas particles. We know the gas particles are always in incessant motion. They're hitting the walls, they're colliding with each other, bouncing off and exchanging energy, changing their direction, and so on. But at the same time, that whole chaotic motion, that business going on between the molecules that we know is always happening, is still described by the same thermodynamic state. We can still say there's this many particles, here's the temperature, here's the volume. And that fact is not going to change if your system is isolated. But as your system evolves in time, it's not stationary. It's going through all of its individual quantum states. What do we mean by that? We mean that at some point, one of the molecules has most of the energy. At another point, maybe a couple of the molecules now have this energy distributed more or less equally. Sometimes the energy is completely equally distributed. And in none of those scenarios is the volume different, is the temperature different, possibly the total energy if it's an isolated system. What I'm trying to say is that a thermodynamic system in its single macroscopic state
undergoes a continuous number of transitions among its different quantum mechanical states. One system, one particle, of what we just had, gives up its energy to somebody else. Everybody gives up its energy and only one particle gains it, which is obviously a very unlikely scenario. And we would like to be able to say mathematically why that's unlikely and what is the actual probability of that happening, which we can do in this class. And so, the system undergoes a constant, set of transitions from one state to the next. The pressure is a well-defined, what's called mechanical property that Terrell Hill kind of stresses what it means to be mechanical and non-mechanical. Pressure is a mechanical property. The instantaneous pressure of a system at any given point in time, if you froze everybody, depends on the specific quantum state. And if we're saying that in a given macroscopic state, determined by a handful of thermodynamic variables, the system makes continuous transitions among its different many-body quantum states, many-body microstates. And when I say this, what I want you to think about is every possible way of partitioning this energy among the different subpieces. Every possible partitioning type is a different quantum mechanical state. If you want to think about it different ways, imagine you have 3 gas particles. At one point, if we forgot about quantum mechanics, and we just thought about classical mechanics, this is one classical mechanical state of the system, or one microstate. In the next instance in time, this particle will be here, this particle will be moving in that direction, and this particle might have bounced off and is moving in some random direction. That is now a different state of the system, a different many-body state of the system, again, classically speaking. Quantum mechanically, we obviously can't tell how fast they're going and where exactly they are. But at the same time, the temperature, the volume, and the number of particles hasn't changed. So the macrostate is the same. The microstate is different. The microstates are evolving and going from one to the other, consistent with the same macrostate. And so the pressure of the system at this point in time would be some number. You can calculate it. Somebody said force per unit area previously. That is what it is. Don't have to worry about what that means with this few particles, but let's not worry about that. The pressure of this system will be something else. And you can imagine, in principle, doing a thought experiment as the system evolves in time, bounces off each other, collides, and so on. You can have a pressure sensor that tracks the pressure as a function of time. And last time we said that what you expect for this system, especially with this few particles, that the pressure will fluctuate a lot. What we're going to say in this class, and we'll say this a lot more, is that the average pressure of the system, when you observe the system long enough, and you average over all of your different measurements, at this point it's this pressure, my instrument is telling me. Now I wait a little bit, I measure the pressure again, here's its value. I do this many, many times, as a system sits on your bench top, for example. And then you average over all the results, giving each measurement equal weight, effectively. No one measurement is more important. What we're going to postulate is that that average value is the thermodynamic pressure that you work with in all of your Maxwell relations and all of that great. But at the same time, what that statement says is that the pressure itself is not a constant thing. Its average value is constant, but at any given moment it's different. It's changing depending on what the molecules are doing. And so let's imagine, kind of abstractly speaking, that we wanted to measure some property called G. G doesn't have to be the Gibbs free energy, it could be the pressure. And so we say we were going to measure this G observed, the value of the property G, for example the pressure, in my system. And what we're going to do is we're going to make a series of measurements. Let's say with equal time intervals, over a long time, so that the average makes sense. And so what that average value will look like is that dividing by the total number of measurements, you will add up all the individual measurements, G sub A, where A is that measurement number, from some first measurement to some final measurement where you're sick of it and you think you're cool. You can be done at that point. This is the average value of the parameter that you'll observe. And so G of A is the value of G, some property like pressure, on observation A. Where A is some number. Now, if we wait long enough, you might be able to convince yourself, or at least you'll have to take it as it stands right now,
that we expect that the system will pass through all of its quantum mechanical states consistent with the macroscopic state. If it's an isolated system with some volume and some number of particles, we expect that the system will, if you wait long enough, you wait a macroscopic time that is infinitely long compared to the microscopic times of molecule motion and collision, that you imagine that it might pass through every possible way of colliding and distributing this energy. It will visit every one of its quantum mechanical states, so every one of its many-body states. And that when you let it visit every one of its quantum mechanical states, this average will be a well-defined quantity and it will make sense. Now another way to rewrite this is to say the following. Let me group these observations in a specific way. Let me just say, let me now sum, not on the number of observations, but on the number of quantum states. This is quantum state, or many-body state, given by the label nu. So this would be 1, so on. 1, and how many of them are there? How many quantum states are there going to be? Many, whatever. Leave it as is. Some number. Possibly infinite. 1 over n, the same as before. I'm just going to write this down and we're going to think about this. And we'll convince each other that this is correct, that the two are actually equal. Multiplied by the number of times, or the number of times that the system was actually found in quantum, let me say microstate, in microstate nu. Whatever that is, microstate 5, microstate 7, however you enumerated them. Times the value of G in that specific microstate. This is basically the frequency with which the system visits that specific quantum state. So what this is saying is, instead of just adding up all of the values and dividing by n, if I make a certain measurement, the system at that point will be in a specific quantum state. If you knew what that quantum state was, you could say, okay, this measurement, the system is in quantum state 1. On the 10th measurement, the system somehow is again in quantum state 1. Then the next measurement is in quantum state 100. And then measurement 57, it somehow comes back to quantum state 1 again. And then what you would say is, let me, instead of summing over the number of observations, sum over all the possible quantum states and to say, this is how many times I caught my system in that quantum state, divided by n, multiplied by the actual value of this parameter, whether it's pressure or something else, in that quantum state. And we just made the statement that this number has a very well-defined meaning and value in a specific quantum state. And that in this particular case, the system just undergoes this dance of different quantum states and transitions and so on, and you just happen to catch it at some state. And you're adding over the observations. Here we're saying, let's reverse this a little bit and just group our observations and to say, observation 1, observation 37, observation 1005 happen to be in this quantum state. These 7 or 5,000 observations happen to lie or find the system in that state. And when you do this, you basically arrive at the same number. You've just grouped them differently. This can also be thought of as the frequency with which the macroscopic system, and when I say macroscopic, what I really mean is many-body, visits microstate or quantum state nu during the total measurement period. And so, what this means is that the number of times you found the system in that quantum number of, or the number of times that system was found in this specific microstate, divided by the total number of observations that you made, can be thought of as the probability that the system at any given moment is found in that specific microstate. This is the same idea as throwing a coin many times. If you threw it a lot of times, you would find that half the time you get tails, half the time you get heads. All you did was you counted the number of times you got tails. You divided by the total number of times you threw the coin. And then we associate that number in the limit as the number of trials goes to infinity as the probability that the coin will land either on tails or heads. The idea is exactly the same. You count how many times the system spends in a specific quantum state, assuming you know how to identify these different quantum states. You don't need to worry about that. We divide by the total number of observations, and we associate this product as the probability that the system is found in quantum state nu times the value of the parameter g in that quantum state. And if you know how to calculate this quantity, and you know what the quantum states are, you effectively have the power to calculate the average value of any parameter, including the pressure, including the energy if the energy can fluctuate, or the number of particles if your system is open, like a glass of water on a benchtop that can evaporate. This general procedure, if you take it far enough, mathematically speaking, which we will, allows you to do that. And so the whole central question becomes, how do we get this? How do we obtain the probability that the system is found in a specific quantum state? Because if I know what that is, and I can enumerate all of my different quantum states, I can calculate the average value of anything if it assumes different values in different quantum states, like the pressure in the cartoonish 3-particle system that we talked about. So if that system was classical here, because we're able to count over the different microstates, we're talking about a discrete, quantized quantum mechanical system that smoothly transitions into the classical formulation, which we'll do later on in the course, which is a reflection of something called Bohr's correspondence principle. So let me just set up where we're trying to go. It is highly impractical to basically do a measurement every single time. You want to be able to calculate some of these things. And to calculate some of these things, you need to know what the probability to be found in a specific quantum state is. And to get there, we're going to use the device called the Gibbs ensemble method. And so this is where we're going to. This is section 1.3 in Terrell Hill. Specifically, it's something called the canonical ensemble, which we'll have a lot more to say about this. And so let's set this up, and then we'll break, and then we'll continue tomorrow. Because again, I don't want to get too far ahead in this, because the hairy stuff starts tomorrow, as far as I'm concerned. And so this is what we're after. How do we compute this? Because as soon as we know how to compute this, we know how to compute almost everything, as far as statistical mechanics allows us to do. And by the way, I want you guys to keep in mind that this whole idea, everything that we're dealing with, is generally set up to deal with systems of very, very many systems of particles. You know, a mole of particles. And in the limit going to infinity. It's an interesting kind of side point that Terrell Hill, his career actually, he didn't just write textbooks. His career was trying to understand how statistical mechanics changes when you go to very few particles. For example, you might, I'm sure you all know about the fact that computer parts are getting more and more miniaturized all the time. The ideal is to have, for example, a transistor, that is one of the main parts of a computer, be made up, for example, of a single molecule or a single atom. Well, now you're dealing with very small particles. And it turns out that all this business of statistics of large numbers starts to go to hell. And all sorts of crazy things start to happen, like fluctuations become enormous. The idea of storing a unit of energy of 1 or 0 becomes problematic because the probability that it'll go from one to the other starts to become a lot more important. And so Terrell Hill's work was on small number statistical mechanics, which is its own field. Everything that we're dealing right now is implicitly saying we're dealing with a macroscopic system with a mole of things, or multiple moles of things, or m being really large. Okay, so the Gibbs ensemble method. Kind of in a surprising fashion, Erwin Schrödinger wrote a statistical mechanics book that is really thin. It's also a Dover edition. You may want to buy it just for the beautiful Schrödinger picture on the front page. It's cheap, but it's harder to read than Terrell Hill. So I don't think it's a good educational tool, at least at this level. Maybe when you guys finish this class. He spends the first chapter, because this is him like delivering lectures in 1924, kind of, or 1925 or something, soon after the birth of quantum mechanics, where statistical mechanics was still relatively young. And he goes through and he compares two different ways of dealing with statistical mechanics, one that he calls the Boltzmann method and one that he calls the Gibbs method. And he very quickly makes the argument that the Gibbs method is highly superior, which is why that's the only thing that we'll hear in this particular time. And by the way, even though statistical mechanics was young back then, it is now highly mature, and I should kind of augment that statement with equilibrium statistical mechanics. That is to say, when things don't change with time, where the average pressure does not change with time. The pressure at any given moment is different, but the average is not changing with time. If the average is changing with time, you're talking about a non-equilibrium system. Non-equilibrium thermodynamics is extremely difficult, still very much undeveloped, or at least partially developed, and not nearly as mature, but the statistical mechanics or statistical thermodynamics can be put on par with quantum mechanics, classical mechanics, a real mature, extremely important subdiscipline of science overall. So it's not just, we're not talking in, small specifics. This is grand enough to have affected every possible, subfield of science, whether it's earth science, geology, astrophysics, chemistry, and so on. Particle physics. Okay, so Gibbs ensemble method. Let's imagine this kind of, fictitious device. We watch our system as it evolves in time, for example, one way to do this. And let's say you had some kind of godlike power that you can freeze time. Say, okay, here's my observation at this particular time. Let me freeze time, take a snapshot of the system, take that snapshot, and what I mean by that is replicate the system, make an exact copy of what the system looks like at that time, set it aside. Let the system run, freeze time again, take a snapshot of the system, set it aside. And do this many, many different times. And ultimately what you'll get at is a huge number of identical macroscopic systems, all described by the exact same macroscopic parameters like volume, temperature, number of particles, but all in a completely random quantum mechanical state that you happen to catch the system in. And we're talking about the fact that the system constantly makes transitions among its different quantum states. And so now you have a collection of this replica of the system in a specific quantum state. That assembly of systems, of replicas of your true thermodynamic system that you've now multiplied fictitiously and theoretically is called an ensemble. An ensemble is a collection of identical systems, each one of which is representative of your one true system sitting on your benchtop, but happen to be caught and frozen in a specific quantum mechanical state. That's the mental device with which we'll be dealing, on which all of our math will be based on, allowing us to do the calculations that we need to do. So what do we mean by this? The specific ensemble that we're going to be talking about is called the canonical ensemble. What is it? Canonical ensemble is a collection of a large n goes to infinity limit number of identical thermodynamic systems, in this case, same temperature, same volume, and same number of particles, and we'll have more to say about this. Identical number of identical thermodynamic systems, all in different microstates or quantum states. But the same macro state, because these parameters are the same, representative of your one true real system, of the true experimental system of interest. This ensemble idea is general in that it requires a number of replicas, identical replicas of the same system. Let me stop talking and let you finish writing. And I haven't said anything that Tyrrell Hill hasn't said. In fact, we're following Hill quite closely, but I'm drawing from a couple of different resources to pull it all together.
I do think Hill does a very good job of introducing this, even though it might take a couple of times of reading it, which, by the way, I strongly recommend. It's not good enough to read something and be like, well, I didn't get that, moving on. Most of the time you don't get everything when you read something complex. And so really, you read it at least another time and you'll feel much more comfortable. You've already thought about a couple of things, and then you're now thinking hard about the few things that you didn't get the first time. Canonical ensemble specifically refers to this condition, that I'm talking about a system that is subject to some constant temperature, that has a fixed volume and a fixed number of particles. So this is not an open system. It's not a system free to evaporate. It's not a system that can change its volume or respond to outside pressure, but it is a system that can exchange energy with its surroundings. That's what we mean when the system is at a certain temperature. That is to say, we imagine our small system, small within reason, a mole is small as far as we're concerned in this particular case, in contact with some enormous temperature reservoir, like the universe, like the rest of the environment. For example, you have a box with thermally conductive walls, but it's locked so that more particles can't escape, and it's just sitting on your table. Because it's sitting in this enormous reservoir of heat, the temperature is maintained constant. But at any given point, it might lose a little bit of energy through its thermally conducting walls, and it might gain a little bit of energy. And so the system itself, the thermodynamic system, might look like this, the one that's actually relevant for your experiment. It has a certain volume and a certain number of particles, and the walls are heat conducting, but they don't let the particles out. And it's sitting in this enormous temperature reservoir, or called a heat bath, keeping the system at a constant temperature. And Hill does an interesting device. He says, imagine that you had a system sitting in this temperature bath, and at some point in time, you took the snapshot, and you made a replica of the system, and you put it somewhere else. Here's my first system. Put another replica and put it here. Same temperature, same volume, same N. Same temperature, same volume, same N. N being number of particles. And you kept replicating this until the total number of systems became large. Let me just say this N is now, I mean something different by it. This is number of systems, number of replicas. Maybe you should say N total. Or this is number of particles in a given system, number of molecules. So here's the idea behind this. We caught our system in a different quantum state every single time. Yes, it's the same macroscopic state, but how the energy is distributed among the different particles in a given system is different among all these different replicas. They're replicas of the same thermodynamic macro state. And then if we could count and say this many systems are in quantum state 3, that many systems are in quantum state 57, this many systems are in quantum state 5. That fraction of systems that are in a specific quantum state, that is to say this guy might be in the same quantum state or not, and given that you have many systems, you might expect to find more than one system in a specific quantum state. The fraction of systems, for example, 2 systems in quantum state 2, divided by the total number of systems, which might be 1 billion, that's the probability, effectively, of finding your one thermodynamic system in a specific quantum mechanical state. And our job then becomes, how do we quantify this probability? How do we work through this artificial device of getting at this number that is representative of the one true system from this conceptual device? It's really nothing more of this ensemble. And again, the idea of Hill's, or at least how he explains it, is that now, once you've made this what he calls a supersystem, this collection of a bunch of identical macroscopic replicas, you place thermally insulating walls around the whole thing. That is to say, now energy cannot be exchanged with the outside, but energy can be exchanged among the different systems so as to keep the temperature constant. When temperature is constant, it means heat can flow in and out, but the temperature will stay the same. When the energy is constant, nothing can go in and out. This is a case where the temperature is constant. The energy staying constant is a different ensemble called the microcanonical ensemble that we're not going to talk about just yet. And what you think about this is that there are so many systems here, all at the same temperature, that for any given one system, the rest of them serve as this heat bath, as this reservoir, such that energy cannot leave outside of this super system, this construct that you've created, but among each other, the temperature is the same, and each one of them sits as if they're surrounded by everybody else, giving you this large, enormous heat bath. Yeah, Steph.
They can't exchange energy between each other, or they can?
They can,
Okay.
because otherwise they would not be able to keep the temperature constant. In that case, the total energy of each system would be constant. And there is that ensemble, it's just not the one we're dealing with.
So that's the grid that was referred to in the text, like they're physically bound to each other, so
They're not necessarily physically bound. And by the way, a couple of things I wanted to say, and you just made me realize. In the example that we were doing before, where we talked about kind of the basic idea of a many-body quantum state, where we had these three oscillators, and we had a total number of energy, and we had a way of distributing it among different kinds, and every possible kind corresponded to a different quantum state. And then we said that the total energy of the system, the energy of the many-body system together, is the sum of the individual oscillator energies. When is that not true? What does that assume?
It's an isolated system.
Isolated in what sense?
It's not in contact with the surroundings.
Okay, it's reasonable. Other guesses? Or thoughts? When would the idea that if you took a bunch of systems and you added their energies up, you get the total, when does that start to break down? That the total is the sum of the parts. What do you think that assumes? Of the three different oscillators.
that they're equal to each other.
They were equal to each other, but that's not quite what I'm getting at. So for example, a gas of ideal particles, or ideal gas particles, would be the kind of system where the total energy is the sum of the individual energies of each ideal gas particle.
When their environments are the same.
Not quite.
Maybe
Yeah.
when they're not, individual particles aren't interacting.
When they're not interacting. That's exactly right. When they're interacting, you cannot say that the energy of one is not affected by the presence of the others. And so each individual energy then gets modified by the fact that it's interacting with something else. So a gas of water molecules, that would be a bad approximation to make because water molecules hydrogen bond, you have dipole interactions which are long-range interactions. And so that's not a good idea. This whole idea assumes that the systems among themselves are very weakly interacting. That's an artificial circumstance that we can always set up. For example, by putting them far apart from each other. This is again something that Terrell-Hill doesn't mention, but Schrödinger in his little very tiny StatMech book does actually spend a few pages talking explicitly about. And so that's something that's worth keeping in mind. Okay. I think I'm going to stop here and I'm going to pick this up, pick this right up on Friday. If you want to get ahead of where we're going, section 1.3 in Hill. Thank you guys for coming, I appreciate it. And we will get this recording out to all of you. And